First of all, let me thank you all for your time and availability and for having me. My name is Nicolò Cosimo Albanese. I am a data scientist and a machine learning engineer in Amazon Web Services, and I'm based in Milan, Italy. And today we're going to talk about online hallucination detection in RAGS solutions. First of all, we all know that large language models are reshaping industries. They are changing the way we work and the way we access information and interact with data, and they are doing this in a very disruptive way. Nevertheless, they present limitations. So when we all know by experience that when we ask a question to a large language model, we don't really have a way to say whether the answer is correct or not. And in fact, we are only able to evaluate their outputs only when we know about the subject. So if we know about the topic, we are able to assess the quality of a response. Otherwise, we are pretty blind. And moreover, we all know that, of course, all models have problems in detecting and talking about events that occurred after training. They have difficulties in retrieving rare or uncommon knowledge, and they all come with the so-called hallucinations. So hallucinations is a broad term used to describe all types of errors related to text generation, so manufacturing incorrect responses, incoherent responses, and anything that might be, let's say, wrong in the generation process. And in the context of, let's say, enterprise search, enterprise application, Retrieval Augmented Generation, or RAG, address these challenges. And RAG combines the generation process with retrieval. In fact, when a query is received, relevant facts are retrieved from a validated data source. It can be an external data source or an internal and proprietary one. And this information is used to enrich the prompt and generate a contextual response. And of course, by providing validated information inside the prompt used to, let's say, used to generate contextual responses, of course, this mitigates the generation of factually unreliable responses, but still, RAG solution might hallucinate. And there is still the problem of detecting hallucination inside RAG. Moreover, there is an underlying problem in terms of user experience, which is often overlooked. And the problem is that RAG promise the user to, let's say, allow him to perform factual checks on the response using the provided context. And the context often comes with links to be opened and read. And here the problem lies in the fact that if we are asking the user to factually check manually all the sources, we are basically going back to a search engine. So we are still not giving, let's say, trust to the large language model. We are not allowing the user to trust the model response, but we are saying, please check the links. And this, again, is going back to another type of application, which is the search engine. So what is the problem statement? What we are trying to do is to increase trustworthiness and foster adoption of RAG solutions in the enterprise. And to do so, we have to meet a series of criteria. So we want to create, let's say, an hallucination detection module that must be performant. So it has to work. It must be able to detect hallucinations with high accuracy. Ideally, it should work online because we want to be able to provide an evaluation during the conversation. And we don't want to, let's say, validate responses post hoc and run a batch and provide an analysis a posteriori. We want to do that in real time when the user needs this validation. Third, it must be scalable. We want to create a REST API that can be queried on demand and meet workloads. It must work on multiple domains. We don't want to have a module or an application that is tailored, let's say, on the healthcare or the financial domains. it must be cost effective to meet non-functional requirements. So most applications start with MVPs, minimum viable products, and we want to be able to embed such a solution in a cost-effective and way, reducing also time to market, because we must also be rapid during these developments. And finally, it must be model agnostic. So there are many models, many large language models, and they power all sorts of applications. And we don't want to, let's say, develop a module that is tailored to a specific large language model. Now, let's dive deep into related work. And we discuss some of the related work in literature, because later we will use part of this as reference to compare our methodology. So at high level, what we can do is we can divide the approaches to hallucination detection into 3 or 4 main principles, let's say, underlying idea. And the first, if we start from the bottom of the presentation, the first, let's say, approach is similarity-based. So the idea is to compare generated text with a ground truth text and assess the similarity. And if the similarity is low, it might suggest that the generated text then is hallucinated, because it is so different from the ground truth. And if we go above, we see that other approaches are based on training or fine-tuning models to be, let's say, judges and really verify whether generated text is hallucinated or not. And finally, we have a token probability based approach. So let's discuss this in detail. Self-check-GPT basically uses it uses the output probability associated to the autoregressive model. So the output probability of each token to assess whether the answer might be hallucinated or not. And the idea is that if we repeat the same prompt multiple times and we sample different answers, and based on their probability, their weighted probability, we can assess whether they might be hallucinated or not, because factual responses might be repetitive, so we might obtain the same probability distribution as output. But if we get hallucinated response, they might be different one from another, they might be contradictory, they might diverge, and so we can observe this through probability associated to each token. And finally, RAGS, it is a framework that allows to evaluate RAG in an holistic way. It assesses both, let's say, vector store, the search engine, and the generator part. And the concerning factuality, what it does, it's through prompt engineering, because it is a prompt engineering based method. It asks the model to sample different sentences from the generated text, and then provide an output which is a numeric value from 0 to 1, assessing factuality as the ratio between the number of contextual sentences and all the inferred sentences. And when we also provide this table, we also want to deeply describe how they can meet or cannot meet, let's say, the requirements that we discussed above. For example, the similarity-based methods, it is something that we could hardly use online, because when we use a similarity-based approach, what we need is a ground truth, because we want to compare the generated text with a ground truth. So it will be hard to implement these, let's say, this type of solution for an online setting. And in fact, later we will use BERT score as a reference. And what we do is that we compare the similarity between the generated text and the context, because in an online application, we would not have a ground truth. Concerning the other methods based on training, so training requires data, and data in this context means involving subject matter experts using their time, manufacturing a validated data set and using that for fine-tuning. So first of all, it will be time consuming and expensive, but also we must consider that fine-tuning is domain specific. So let's imagine to be in an enterprise and introducing a RAGS system. And let's imagine that the enterprise is introducing the RAGS system through an MVP on a subset of documents, let's say in a legal domain. And after an experimentation, they want to open the solution to more domains, like the manufacturing, the marketing, but they will be different domains. So, an hallucination detection based on fine-tuning might need consistent and continuous retraining to be effective on new domains. So it will also pose some challenges. And this is an overview also to discuss how these solutions could be applied online. And finally, the last and most important point is these approaches provide a numeric output. And it is not a binary score saying the sentence is hallucinated or not. It is a numeric output. And this, let's say, might pose a challenge in terms of interpretability. Because when we say factuality is 0.7 or 0.8, what does it mean? What is the right cutoff to consider whether a sentence is hallucinated or not? This is also something that we should look for. And this also requires training, because it means that we have a ground truth, we can validate the output numbers and find a cutoff. So there is an underlying also procedural, let's say, challenge in converting those numbers into a binary information that is actionable for the user. What we did was, first of all, we want to assess a prompt-based methodology, and in-context learning methodology. In-context learning means that we provide examples with explanation inside the prompt. And what we did to test this approach was, first of all, we gathered openly available data, and we did that fetching books from Project Gutenberg in different domains, from politics, science, and history. We manufactured a synthetic data set. We divided the books into chunks of 2,000 characters each. And for each chunk, we got the context, let's say, synthetically generated question, and both a factual and an hallucinated response. And we could gather around 4,500 answers. And the dataset was balanced because we had a good ratio between factual and hallucinated responses. And then what we did is we applied methods from literature, in particular a similarity-based method and a prompt-based method. And we compared the approaches from literature with, let's say, an in-context learning approach, and that we wanted to validate. And importantly, we tested our approach on multiple large language models, all available from the Amazon Bedrock platform on AWS Cloud, but they are just API calls, so they could be replaced with any model. And another important aspect is that, as we said, BERT score and RAGS provide a numeric output. So since we wanted to compare these approaches with our method, which is binary by design, we had to find a cutoff to determine whether they were, let's say, evaluating an answer as hallucinated or not. And we did that by maximizing the UDNJ statistics. So we found a cutoff that was maximizing performances on the binary detection task. Concerning the results and the prompt that we used for in-context learning is available inside the paper. And so we compared, let's say, our methodology, as we said, applied on different models. And we see from Amazon Titan to Anthropic Claude V2. So we did test multiple models. We also tested an Anthropic Claude Instant, and with similar outcomes, 0.9% accuracy in hallucination detection. So we tested 5 models, and we tested the BERT score and the RAGS approach. And what we could find is that we can outperform these methods from literature by at least 11% in F1 score. And we achieve this through prompt engineering. And when we say prompt engineering, we did not use in context learning in a way that we added examples in the prompt from the context, from the data sources, but we added very general and very, let's say, scalable examples, which are very simple and very general, just to provide the LLM with a logic, the logic that we wanted him to implement in the evaluation task. So in conclusion, our key contribution is to, let's say, propose a lightweight, accurate hallucination detection module for RAGS. And we did develop this for our customers. We do use it in enterprise applications with high performances, and we use it with different models depending on the functional and non-functional requirements from our customers. And so our approach does not implement any sampling bias, because we just solicit the responses from model by soliciting reasoning rather than generating statements. We do not sample new statements. We do not calculate probability distributions from the output token probability. We do not apply any tuning or ground truth. So we can scale this in void of ground truth, in void of subject matter experts evaluation, and we can use that for online usage. So this approach is a REST API that can be embedded in any chatbot. And it is simple to build, it is simple by design, so it can also easily integrate it in a workflow. And so while preliminary, what we can prove is that we surely have a potential with this approach, with in-context learning, to provide, let's say, trust and fidelity RAG systems. And of course, this study comes with limitations. So we surely should test with higher numerosity and variety of both data sources and models. And also, what I think to be the highest limitation is, well, this is a prompt engineering based method. So all prompt engineering based methods, they rely on the prompt. So in truth, what happens is that they rely on the ability of the engineer implementing the solution. And to remove this dependence, there are two approaches that can be combined to this idea. The first is to incorporate prompt compression frameworks. That basically what they do is they compress the prompts, trying to reduce their size while maintaining performances. And this is extremely useful. For example, many times I was asked why your prompt has this specific length, or why do you have, let's say, 8 examples in the prompt, why not 7 or not 6? And so prompt compression techniques can really find an optimal, from a mathematical point of view, between prompt length and performances. And this can be combined to abstract prompt formulation frameworks. So frameworks that allow to build, let's say, a prompt, but without writing it, without writing the prompt, and just treating it as, let's say, developing Python code. So in an abstract formulation. And combining these two, let's say, frameworks, these two ideas with this prompt-based approach, we could investigate further on scaling this approach and really removing the dependence from the prompt. Although we also proved while testing that the same prompt, which was a pretty general prompt, was scalable across different domains of the data sources, from politics to science. And we also have practical experience in our let's say, daily work with our customers on this topic, where we follow similar approach. And this concludes the presentation, and thank you.